Okay, today we're going to talk a little bit about trawl surveys in terms of counting fish. Trawl survey basically goes in, puts gear in the water, trawls, nets, pulls them up, counts them over time. This is a place where you can look at different trawl surveys in terms of winter and spring and fall in the Northeast. This is an example of a report here. This is a resource survey report from Cape Hatteras to Gulf of Maine by Noah's Bigelow ship. And just to give you just a sense of what the trawl survey looks like, a stratified random design where they have these different strata and different depth bins, and then they randomize the samples on the inside of that. And so they look at these over time to try and assess the population of fish. For different fish, multi-species, we're going to really simplify this in a R exercise of counting fish via trawl surveys. So we're going to go ahead and I'm just going to put this here and say that we are going to count, simulate fish counting in trawl surveys in 3 different scenarios. Okay, 3 different scenarios. And the idea here is just for you to get a sense for what some of the assumptions are on a trawl survey and how the sampling of a population might change your estimate of it. So the first thing we're going to do is we're going to simulate a flat spatial distribution of fish, and we're going to have a single random trawl sample. All right, what is this going to look like? Well, first thing we're going to do is define our time. Our time vector is just going to be 1 to 40. Sorry, 1 to 40. So that's going to be like 40 years of time. And because this is a simulation, we are going to define a stock that is oscillating over time for some unknown reason. Maybe there's a natural climate pattern, maybe there's an age-structured pattern. We're not sure exactly, but just for the sake of having an oscillating signal, we are going to generate a sequence from 0 to 4 pi, 4 times pi, and the length of that sequence is going to equal the length of time. All right, so what do we have so far? We have time and we have n. Oh, this not shouldn't be p1, it should be pi, number pi. So there's our time. There is our stock for now, which is number going from 0 to 4 pi. And we're going to go ahead and take the sign of this thing. And you'll see what happens. So let's just plot Tm and n. And you can see we have an oscillating signal going from 1 to -1. That's what sine does. But we're going to bump this up above the x-axis. We're just going to add 2 here. Let's run this again. And you can see now our scale has changed. So everything's, going between 1 and 3. So we've just moved this up. And this is going to be our sample. And we're just going to come in here and multiply now this whole thing by 1,000. So this now is going to be, just modifying it, this is going to be our oscillating signal over 40 years. This is going to be the background, what the population is actually doing, and our sampling is going to have to estimate that over time. So I'm going to make a vector here called n_est. This is going to be something that a loop collects, and you'll see what we do here in just a second. So we have to make a space now. This is our element in time. This is stock over time. Let's define the spatial distribution of the stock. Again, this is a flat distribution. So we're going to be using, let's just call this our x dimension. we're going to use a function called runif, or runif sometimes it's called. This is a random uniform distribution where we're going to pull the nth element. Okay, what did I do here? Okay, so I'm just going to set at first x equals 1. This is going to be a loop eventually. So little x equals 1. Let's take a look at this. So this is the uniform distribution. Runif, this is going to ask me how many elements do I want to pull out of a uniform distribution. In this case, the default is min of 0, max of 1. So in this case, I'm saying I want you to pull the first element, the xth element, which is we defined as the first element here, from n. And so if we take a look at our first element of n, I want you to pull 2,000 numbers with a minimum of 6 and a maximum of 14. Why are those two numbers? You'll see in a bit. But let me just run this and just do a histogram of x, and you'll see why it's called a flat distribution, because there's no like bell shape to it or anything. It's just you're just as likely to pull a 6 out as a 14 as a 10. So that is a flat distribution. We can go ahead and replicate this with y dimension. We'll go ahead and run that. And so now let's go ahead and plot x, y. Put our x limits on there and our y limits on this. Okay, if we plot this thing, this is going to be our spatial distribution of our fish over our grid from 6 to 14, 6 to 14. That's 2,000 points with a flat distribution. We'll change that coming up, but so far we're going to start with a flat distribution. So I can keep running this over. If I run it again, you'll see that the points change a little bit. Keep running it over and over again, but again, it's all a flat distribution, 2,000 points, because that's the... So if we, let's see, go ahead and make this a formal for loop now. Let's indent these. For x in 1, 2, the length of tm. So that's 40. We are going to do these commands. Okay, so what happens in this x loop? X is going to count from 1 to 40, and then we're going to pull the xth element from n. Right, so the x equals 1 will pull 2,000, x equals 2 will pull 2,300, x equals 3 will pull 2,600. That's how many numbers we're going to draw. And we'll go ahead and run this. You know, let's do this. Main equals x. So it's making a bunch of plots. So the 40th year, that's what it looks like. I can go back in time with this, 39, 38, and you'll see there's fewer and fewer points because we're following that sinusoidal pattern, and then they'll get more and more points, and then you'll see them get sparse again, and that's what we're pulling those points and we're putting them in space so we can see that sort of up and down. So this is in space, this is in x and y, and again, remember we can plot our tm and n, right? So that's basically, we're pulling 2,000 points, putting them in a flat distribution for every time period. You can see the population going up and down here. Okay, here we go. What do we need to do? So now what we need to do is pick a random spot to trawl. So we need to set our trawl size. So equals 0.5. I'm just going to start with 0.5, so that's 0.5 units. We go back to our space here, so it's going to be, this is 2 units here from 6 to 8, so it's going to be half half wide and half tall. And then we need to locate it. So the location of our trawl in the X dimension, again, we're going to use a run if. We want to pull one number from a distance that has limits of 6 to 13, right? So if we run just this bit here, oh, this should be 14 actually, 6 to 14. If we just do this, we're going to pull 13.8. That's going to be the center of our trawl. So that's going to be over there. We run it again, 9.4, so that'll be in here somewhere. But then what we're going to do is we have to account for the size of the trawl. So we have to do the lower limit is going to be 6, but remember our trawl is going to extend half on either side. So we're going to do trawl plus trawl size and 14 minus trawl size. Okay, and let's just mimic this for location Y. Right, so, oh, I gotta run trawl size first. Okay, so we have a location in the X direction and the location in the Y direction. Okay, so X would be 7, X would be 10, Y would be 7, so the trawl would be in here somewhere. And let me just show you what that would look like. So, because we can actually plot a rectangle, we'll use a function called rect, which is the location of X. Let me just show you this a second. Rect is to draw a rectangle on a map, so we need the X left corner, the Y bottom, the X right, and the Y top. So our X left is going to be our location X minus the trawl size and then location Y minus the trawl size, location X plus trawl size, location Y plus trawl size. Okay, let's click on our plot here again, and you'll see I'll put a rectangle on here. There's the rectangle, right? So that's where it came out. So that's centered at 10.6 and 7 point something, and we just push the rectangle. So we're going to count all of these on the inside of this point. So how are we going to count those? Let's do it this way. We can make a catch index. We just want to know how many of these actually fall inside that bound. And so we can use the which command. So we want to know which X values are greater than or equal to this thing. So remember that defined this bound of the box over here. So we want to know everything that's greater than that in this direction. And we want to know which things are, let's just change this to less than, plus trawl size. So that's at this line, that's the defined. So we want to know which of our X values are defined by between this line and this line. And we're going to, oops, this should actually be an and. So we want to know whether or not this is true and this is true and greater than or equal to, we want to know if Y is greater than or equal to the location in the Y direction. minus trawl size. So that's defining our bottom line here. So moving up, we're saying, I want to know everything that's greater than this location minus this trawl size, which defines this lower line here. And I'll just copy this. This is going to be plus, less than or equal to. So we should get an index. Catch end now. These are the observations in X and Y, the 58th observation, the 91st observation, the 102nd observation that fall within these bounds here, So let's just do this here. We can add by visualization. Let's just do points, which is adding points to a graph now. X, which is all our points defined in X space. Catch end. Whoops. Y. Catch end. Color is going to be red, and PCH equals 20. That's going to make it our point character solid and red. There they are, right? Those are the ones that are found on the inside of that boundary. So those are the ones that we're catching, and we're going to count them now. How are we going to do that? Well, we're going to append. Remember, we're trying to estimate this. So how do we estimate that? Well, we know the length of our catch end is the number of fish that we caught of this single species. So what's the length? We caught 38, so there's 38 red points in here. Those 38 points were in, what were they in? They were in our trawl size. Well, what's the area of the trawl size? Well, we define trawl size as a central point minus half a unit this way and plus half a unit this way. So our trawl size is the total area swept here is trawl size times 2, so that gives us the length of one of these sides, and we're going to square that. That gives us the area. So if we just run this little thing here, that gives us an area of 1. That makes sense because the length of this side is 1, the length of this side is 1, 1 squared is 1. So we can call this 1 square kilometer swept. But we have to now figure out that if we caught 38 of these things in 1 kilometer, how many kilometers are there here? Well, we go 6, 7, 8, there's 2, so there's 2, 4, 6, 8, and 8 this direction. There's 64 kilometers here on this thing. So I have to, if I want to figure out how to, I have to do 64 divided by this thing and multiply that times my catch end. So if I said I caught 38 of these things, if I trust the distribution of that, how many are out here? If I run that, I get, my guess is 2,432. Now I know that because this is x equals 1, there's 2,000 in here. So it's not a bad guess, not a bad guess. So we're just going to make this our n guess. That's our guess. So we'll just run that. Then we'll say that our n estimate, which is the thing that we're going to store, remember it's up here, it's an empty object, is going to now equal, concatenate whatever was in n s, the loop before, round before, with n guess. Okay, I think that should do it. Right. So if we start from here, we have x equals 1 in this case. Let's come over here and run this. Oh, ns not found. I guess I got to run that. There we go. Pretend we'll just run the inside of the loop here real quick. All right. Okay. And then I can run the whole loop. So let's come up here, start with ns to come down. And we're going to run 40 iterations of this. Now it's done. There's 40, right? So we can actually march back and say 39, that's where we sampled, 38, where we sampled, 37. Okay, all right. So now we can check a few things out. We can say, all right, let's go ahead and plot our time and our n, type overplot. I'll put 0 to 30,000. So this is now a plot of the true population. That's what it's doing, up and down. And now let's add points to that, which is going to be the time and our estimate using this type of sampling, assuming a flat distribution. Color equals red. Type equals overplot. Let's see how well we did. There it is. Okay, not too bad, right? So just by taking that small sample, 1 out of 64 kilometers, and scaling it up, we didn't do too bad on the estimate. In fact, we can take a look here. Let's do the mean of n and compare these. So what's the mean? The mean's going to be 2,000, because that's on average over time, and the mean of n est. This is over 40 years. What's the average? Not bad, 1,995. That's pretty close. And what we can also do is compute the RMS statistic. Root mean squared error. Root mean squared error is a way to compare the difference between two time series. And this is how we do it. It's called the root mean squared error. All right. So it's basically a difference between n minus n estimate. So if I do that, I'm going to get a 40 differences, right? Because it's subtracting each element in n and n est. And we need to square that. And then I'm going to put parentheses around it, and we need to take an average of the square. And then I'm going to take the square root of that average. So the error is 333 on average. So we're off by 333 on average. Okay, we can run this again. Let's go back up to the top, to the very top. Again, what are the assumptions here? The assumptions are, again, flat spatial distribution. I should write them in here. Single random trawl sample. What else? Fish are always caught by the net. Fish are always caught by the net. Okay, let's take this and we can run it. In this case, we get 333. Very similar. Clear those plots out. Run it again just a couple times, and you'll see that on average 2,000. So not bad. We're doing pretty good. All right. What happens if I shrink the trawl size down? Let's go down to 0.1. So that's really going to shrink the size. Let's see what happens. Okay, you can see that we don't do quite as well in reproducing the time series. Our average isn't too far off. The square root or the RMS error is pretty big, but you can see that, we're just sampling such a small area and then trying to scale it up that, here we sampled a small area, didn't catch anything. Year 39, there's one there. So it looks like that we would have to, there's lots of times here we're only caught one. So the size of your sampling is important. So we can also go back here and say, well, let's make it, instead of 0.5, let's make this 2. So increase the area swept. Our box should get much bigger. Oh boy, we do really well in representing the background population because our swept area is really big, right? We're sampling a huge amount. So, our whole population occupies 64 kilometers squared, and we're sampling, what? 16 kilometers squared. So pretty big chunk. Pretty big chunk. And our RMS error is, only 90, really small in comparison to 2000. Okay, let's come back up here. Just make this 0.5. So that's scenario number 1. What about scenario number 2? This is now going to be a normal, not a flat, a normal spatial distribution of fish. Again, same assumptions as before. All right, so all I'm going to do is I'm going to take this whole thing and I'm going to copy it, put it down here, and all we're going to change is we're going to come up here and we're going to change the distribution of the fish. So let's clear this out. So before we were using run if, now we're going to use our norm. So this is now the normal distribution. The normal distribution. So I'm going to change this to our norm, the normal distribution of fish. And I want to have a mean. It's asking for the mean of the distribution. I'm going to pick it as 10 and a standard deviation of 1. 10 and 1. So what does this look like? So let's clear everything out here. And let's run this again. Let's just do x equals 1 for fun. And I'm just going to run these first couple lines. Oh, this should be our norm. Sorry about that. Run these first couple lines. There it is. So now you can see that the distribution is not flat or evenly distributed, but it's clumped together. And that's because if I do a histogram of x, you can see that I have the normal distribution. And if I do a histogram of y, you can see I also have a normal distribution. And when I plot two normal distributions together, you get this sort of spatial structure. They're kind of in a group. Now they're in a group. So what happens when we pick a random place to trawl and then try to run our same estimators? Let's see. So we'll try at 0.5 and let's run it. Okay, here's what our true population is. This is what our estimator is now. When we don't know anything about the spatial structure of the stock, we're just randomly sampling. You can look back and see that's where we sampled and counted there. That's where we sampled and counted there. So you can see that our estimates inside our box are not really capturing the variability. Not really capturing the variability. Right? So if we go to our last plot, there it is. You know, when it gets lower, and when it's higher, but it's really spiky, really, really spiky. So we might need to increase the trawl size, maybe to 1. And let's see what happens. Again, so you can see our mean here was 2,000. Our estimated mean was higher. Our RMS error was bigger than our mean, which means our error is way bigger than our estimate. That's not so good. Let's see. Do the same thing here with a little bigger trawl size. Yeah, still not so great. Still not so great. So, increased it a little. We're still overall overestimating the trawl size because, most of the fish are in here. They're not out here. But we have a randomized design. Yeah. Okay, which leads you to plots that look like this. They generally get the trend, but not really. So if there's some spatial structure, that means we need to think about how we make our stock estimates, how that actually happens. Okay. All right. Let's increase the trawl size now to 2 and see what happens. All right, now it looks like we're systematically overestimating the stock. And if you look at the sampling, you can see why that would be, is because wherever we are taking this density and we're applying that density to all these other places. So this would happen if, say, your sampling was really focused on where the fish were and not where the fish were not. So we're now oversampling this distribution, and we're taking this density and applying it to this whole 64 square kilometers. And because we're doing that, that means that we are generating estimates that are systematically higher than what the true background is. Because we're sampling where the fish are concentrated, and then we're applying that concentration to places where there's no fish. Again, we wouldn't know that unless we knew what the spatial distribution of the stock was. All right, let's try one more example. So we're going to do now a normal spatial distribution of fish, but clustered in groups. Same assumptions as above. All right, so I'm just going to take this whole thing. All we're doing is we're changing the spatial distribution. Instead of doing a normal distribution, we're going to introduce a new variable. Remember, this is going to be the location where the fish are. We're going to say that we're going to call something called x means. And that means we're going to sample or permute the number 7 through 13. Y means. I'm going to do the same thing. And you'll see why we do this in a minute. Okay, so what does it mean to permute this? Well, so 7 through 13 is just a vector. That's all it is. So if we permute that, sample it, it's just going to randomly rearrange that vector. You can see. Well, this is going to be these are going to serve as the locations where we're going to pluck down our 2000 or whatever our species are, because X norm now in the mean category, we're going to put these X means, which are these random cores. So if I do X equals 1, let's run this top part and you'll see what we get. Plot this thing. You can see now, why did that happen? Oh, I know why. Happened because I had my standard deviation too big. I'm going to shrink my standard deviation to really tighten. So this is going to be 0.1. Tighten up these distributions. All right, let's do this one more time. There they are. Okay, right? So these are now, our fish are not sort of flat, randomly, flat distribution, or they're not even normally distributed, but they're in these little clumps or schools. And on each time period, these schools move around, but they're still 2,000 points there. There's still 2,000 fish. So what does that do to our estimate? Run the same code. How big is our, oh, let's take our trawl size back down to 0.5. Okay, not so hot. You can see that we have a severe underestimate of this, right? There's actually 2,000 on average. We're estimating half of that. Our error is huge in comparison to what the actual, the root mean squared error is huge in comparison to the known population size. And if you look at the sampling, you can see that. A lot of times it's out there and we just miss them. And that's because this sampling, this random survey sampling, doesn't know anything about the spatial distribution of the fish. And so you miss them a lot. Now, one way to get around that would be to say, increase the trawl size. Back up here to the beginning. Sweep these plots out. Okay, it's still not great. Now we're overestimating on average, and you can see that, okay, you know, we're starting to get one of these, but then we're applying this density to the entire area, and maybe that's not so good. What if we do this even higher? Yeah, well, that's not so bad at all in comparison to the other ones. And that's because we really made our sampling much larger. And we got a couple of these big clumps in there at a time. And then, you know, we could apply the density to the other squares here, and it was a pretty decent estimate. But we really had to increase our sampling size. And we really had to increase our area. So instead of 1 across, you know, now we've got 4 across. So instead of 1 square kilometer we're sampling 16 square kilometers, which is a lot more effort. So when you have spatial structure to the stock, it's much harder to estimate, and you can see how that might be the case. In fact, we'd have to maybe really increase this thing, maybe 4. We'll see that if we do that, then we're, you know, right on there. And why is that? Because we're actually just capturing everybody. But if we're sampling and we're capturing everybody, that means that there is in fact nothing left to fish, which is a little self-defeating considering what we want to do. Okay, so that's just a really quick overview on the impact of the spatial structure on simulated trawl samples.